Okay, so I want to prove this theorem that a principal ideal domain is a unique factorization domain. And so far what we have done is we have defined this notion of a Noetherian ring. It means that it's a commutative ring with 1, always with 1, such that you cannot have a sequence like this. You cannot have ideals I1, I2, I3, etc. that strictly get bigger and go on forever. So there is no infinite, strictly increasing sequence of ideals. Okay. So if you have any sequence that is getting bigger and bigger, then there is an end such that after that stage they're all the same. That's the notion of a Noetherian ring, and we've proved that a principal ideal domain is Noetherian. Okay. Now we'll use this Noetherianness to show that it's actually a unique factorization domain, meaning every non-zero non-unit can be written uniquely up to reordering and up to units as a product of irreducible elements. So that A in R be a non-zero non-unit. And you want to write A as a product of irreducibles. So step 1 would be, or maybe claim 1 would be that let's find a reducible factor. So claim 1 says that A has an irreducible factor, meaning there is a irreducible element that divides it. So proof of claim 1, suppose not. Meaning A does not have any irreducible factor. I suppose A does not have an irreducible factor. Then what happens? Then A itself cannot be reducible. So in particular, so you can write A as a product of two non-units. That's what not being irreducible means, that you can factor it for some non-units A1, B1. Now look, A1 and B1 cannot be reducible either, because, or at least A1 cannot be reducible either, because if A1 was irreducible, then it would be a reducible factor of A. So, note A1 is not irreducible, since it would be a reducible factor of A. Let's not write all that. A1 is not irreducible either, because A has no irreducible factor. That's our assumption. Right? We are going by contradiction. So A1 can be factored as A2B2 for some non-units and this goes on forever. Inductively, you find A2 and then A3B3 and so on and so forth. We get a A1, A2, A3, etc. and B1, B2, B3, etc. all non-units such that A n plus 1 is, A n is A n plus 1, B n plus 1 for all n. So what does that give you? that gives you, look, A1 divides A from here, and then A2 divides A1 from here, and then similarly A3 would divide A2, etc. So what about the ideals? The ideal of A is contained in the ideal of A1, contained in the principal ideal generated by A2, contained in the principal ideal generated by A3, and so on. And furthermore, these are not equal. Why? Think about that for a little bit. These are not equal because B1 is not a unit. If they were equal, then this B1, this other factor, would be a unit. And then this is not equal since B2 is not a unit, etc. So you get a strictly increasing chain, or strictly increasing infinite chain of ideals. That's an impossibility because you are in a PID, so you are in a Noetherian ring. So verify this. I just indicated. R is Noetherian. This is impossible. This proves claim 1. I'm too used to writing Noetherian with lowercase, like Abelian group. It's a show of honor apparently, or Gaussian algorithm. It's like becomes so famous that it loses the capitalization. This proves claim 1. So what you know is that any non-zero non-unit has a irreducible factor. And now, next step, I want to show that A can be, or A is simply, A was some non-zero non-unit in the ring. A is a product of irreducible elements. And the idea of proof of that is that you take this guy, you know it has a reducible factor, so you pull out a irreducible factor. And then you get some other factor. Now if this guy is also irreducible, then you are done. So this guy cannot be reducible. So you can factorize it again. So you can write B1 as some A2 B2 by pulling out another irreducible factor. Now these guys are irreducible. Now if the remaining thing is also irreducible, then you are done. So it cannot be. If you're assuming that A cannot be written as a product of irreducible elements, so you pull out another irreducible factor. So you factorize B2. Now these three guys are irreducible, and then so on and so forth. So if A is not a product of irreducible elements, then this process will go on forever. And then it would lead to these guys, B1, B2, B3, etc., where B2 divides B1. Let's write it the other way. It leads to these elements B1, B2, B3, etc., where B1 is divisible by B2, because B1 is A2, B2, and then B2 is divisible by B3, because it's A3, B3, then B3 is divisible by B4, etc. And so, in terms of the ideals, this ideal would be in this ideal, would be in this ideal, etc. And again, these would be strict containment because the other pieces are not units, they are irreducible elements. And that would give you a strictly increasing chain, which is impossible in a Noetherian ring. So let's write something down. By step 1, this is only a sketch. Write A equal to A1, B1, where A1 is irreducible. So again, let's assume by going by contradiction. So proof. Suppose not. It's easier to just write by contradiction. So A is not a product of irreducibles. Then by step 1, by claim 1, we can write A equal to A1, B1, where A1 is irreducible. So B1 is not. So in particular, B1 is not a unit either, because if this is a unit, then A would be a product of irreducible. Then, product of irreducible and a unit, maybe I should say, and an unit. In all this factorization, the units sort of don't count, right? So if B1 is a unit, then you have written it as a product of irreducibles and a unit, so it's not a unit. B1 is not a unit. So it's a non-zero non-unit, so we can pull out a irreducible factor from B1. A2, B2, where A2 is irreducible. Then what have I got? Now A is A1, B1, and B1 is A2, B2, so it's A1, A2, B2. So B2 is not a unit, because if it was, then I would have written A as a product of two irreducibles and a unit. So B2 is A3, B3, where A3 is irreducible, etc. So verify now. Now I'll just skip a little bit. Verify that inductively. We get a strictly increasing, but this is basically the construction, increasing sequence of ideals B1, B2, in B3. Yeah. B1, the ideal of B1 is in the ideal of B2 because B1 is a multiple. B1 is a multiple of B2. And similarly, B2 is in B3 because B2 is a multiple of B3, etc. And the other factors are irreducible elements. That tells you that these are strict inclusion. Since R is Noetherian, this is impossible, which means that this process has to stop at some point. That's how this finiteness sort of comes into play. So I got a contradiction to this suppose not. So A is a product of irreducible, so this proves. So this shows the existence of factorization, and now you have to prove the uniqueness. Is left as an exercise. It's not hard. I really wanted to show where this chain condition comes into play. And this is written out in the notes. You can take a look. We'll move on to talking about Euclidean domains. Maybe give a couple of examples before that.